Hello fellow peers, my name is Rachel and I want to welcome you to Collision Curriculum AP Calculus AB. Disclaimer, I am in no way, shape, or form associated with the real crash course and this is just my final project for the class. Today we are looking at the hardest topic of AP Calculus AB, surveyed by fellow peers, which is related rates. Fun fact, my calc class had to take the related rates test 3 times before moving on. First of all, what are related rates? To give you a basis, the textbook definition of related rates is the rates of change of 2 or more related variables that are changing with respect to time. Basically, this shows how 2 or more rates, such as how the height and volume of something like, say, water in a tank changes over time, is related. By the end of this video, I hope you're able to understand how to use calculus to find the rate of change of one variable if you're only given the other variable. Still confused? Look no further. Let's break it down. Going all the way back to the beginning, you'll need to understand how derivatives relate to all of this. The first thing you need to notice is the words rate of change, or other variations, such as increasing or decreasing at a rate of blah blah blah, and so on. Breaking down even further, we know that the derivative is basically the slope, which is why you read it as dy over dx. Like the slope, it's the change of y over the change of x. Take the change of the volume of water inside a tank over time, for example. In this case, the change of volume is like the change of y, while the change of time is like the change of x. Therefore, you can write this as dv over dt. The next thing you'll need to understand is the chain rule. The chain rule is used when the variable of the numerator and denominator of the derivative don't agree. For example, say you have d sine of 2x over dx. You can only solve this derivative if the variable is the same. Here, the top is 2x, while the bottom is x. In this situation, the chain rule comes in handy. Basically, you manipulate the derivative into becoming solvable without really affecting the derivative at all. By putting the d sine 2x over d2x, it becomes solvable. However, in order for the overall derivative to not be affected, you need to multiply this by d2x over dx. Then if you simplify this, you can see that the 2x cancels out and you're back to the original derivative. Leaving this unsimplified is actually going to get you somewhere. As you can see, the variables all agree with each other and you can rewrite this as cosine 2x times 2, which just equals 2 cosine 2x. Miss Rachel, how does this even connect to related rates? Ah, young Rachel from last semester, if you were patient, I was just about to get to that. Let's look at an example of a related rates question. Say there's a spherical balloon filled with air. A tube is attached and fills the balloon with more air, thus increasing the balloon's volume by half a cubic centimeter per second. The question is, when the radius of the balloon is 10 centimeters, how fast is the surface area increasing? Before jumping right in to try and solve this, it's very wise to draw a picture first. It doesn't have to be super detailed, as long as you understand what the scenario looks like, you're good. The next thing I highly recommend you to do is to list what's given, what's needed, and what you know about the shape. It's given that the volume is increasing at a rate of 0.5 cubic centimeters per second, which can be translated into dv over dt equals 0.5 cubic centimeters per second. What we need to find is the rate of change of the surface area, which is d big T over d little t. Usually, the equation for the volume of whatever the shape mentioned is provided for you in the real AP Test FRQ, so don't bother memorizing the volume equations for shapes such as cones, cylinders, and spheres. In this case, the shape is a sphere, and the volume of the sphere is equal to 4/3 pi times the radius cubed. The question is asking us to find how fast the surface area is increasing once the radius of the balloon reaches 10 centimeters. Now you might be wondering, they gave us the radius and the volume, so where does the surface area come in? Let's have a quick geometry review. The surface area equation for a sphere is 4 pi times the radius squared. The volume of a sphere, which we already mentioned, is 4/3 pi r cubed. What if you forget what the surface area equation is? No worries. Take the derivative of the volume equation using the power rule. If it's done correctly, you can see that the derivative of the volume is actually the surface area. Back to where we were, we now know that the surface area, or capital T, is 4 pi r squared. You might also want to notice that the variable used in both surface area and volume equations is r, or the radius. This is important to realize because while these equations are in terms of r, the rates that are given and asked for are in terms of t, or time. As you can see, we have different variables, and you know what that means? That's right. It's time to break out the chain rule. First, let's try to find a way to get d big T over d little t. We can make this equal to d big T over dr times dr over d little t. d big T over dr can easily be found because we already know the surface area equation. dr over d little t, however, will need a few more steps of chain ruling. We can find dr over dt using the chain rule method for dv over dt, which was already given as 0.5 cubic centimeters per second. Once you manipulate the equation into dr over dt equals dv over dt divided by dv over dr, you can now solve for dr over dt and substitute it in the original chain rule equation for the surface area. Now, what you get is 1/2 divided by 4 pi r squared, which equals 1 over 8 pi r squared. Going back to the original chain rule equation, you now have d big T over d little t equals 8 pi r times 1 over 8 pi r squared, which is equal to 1 over r. Now, as my wise AP Calc teacher would say, it's just basic algebra. The radius is already given, so now just plug 10 in for r and voila! The answer is 1/10 or 0.1 centimeters squared per second. A little side note, always keep track of the units in the problem. Alrighty, now that we've gone over the basics of related rates, let's check out this FRQ from the 2002 AP Calculus A/B test. A container has the shape of an open right circular cone as shown in the figure above. The height of the container is 10 centimeters and the diameter of the opening is 10 centimeters. Water in the container is evaporating so that its depth h is changing at a constant rate of -3/10 of a centimeter per hour. As you can see, the problem gives you a note saying that the volume of a cone of height h and radius r is given by v equals 1/3 pi r squared h. First of all, let's write down what's given. H is equal to 10 centimeters, d is also equal to 10 centimeters, and dh over dt is equal to -3/10 of a centimeter per hour. Next, write down the given equation of the volume for future reference. Let's take a look at part A. Find the volume V of water in the container when h is 5 centimeters. Indicate units of measure. First, let's recall the formula for volume. Part A only gives us the height of the water, but the equation of volume requires two variables, the radius and the height. In this scenario, you should always express the equation as a function of one variable. To do this, we need to look at the geometry of the model. Because the diameter of the opening is 10 centimeters, we can conclude that the radius of the opening is 5 centimeters. Because we know that this is a right circular cone, we can also conclude that by connecting the ends of the radius and height, you get a right triangle. Remember back in geometry where you looked at similar triangles? Well, me neither, so let's look at them once more. Say you have a right triangle. If you cut straight down the middle of the triangle, the smaller triangle will still have the same angles as the original triangle by the reflexive property of congruence and the corresponding angles theorem. Basically, this means that the smaller triangle will have the same leg length proportions as the bigger triangle. Let's go back to our triangle from the right circular cone. The radius and the height are the legs of the triangle with lengths 5 and 10 centimeters. Because the radius of 5 is half the height of 10, we can conclude that the radius of the smaller triangle made by the water inside the container must also be half the height. Now we can rewrite r as 1/2 h, or in this scenario, 5/2. Oh ho ho! It's just basic algebra! The volume equation can now be expressed as a function of the variable h, which is given as 5 centimeters. Now we have v equals 1/3 pi times 5/2 squared times h. Time to plug 5 in for h, and now the volume is equal to 125 pi over 12 cubic centimeters. On to part B. Find the rate of change of the volume of water in the container with respect to time when h equals 5 centimeters. Indicate units of measure. The first thing you should immediately notice is the verbal expression for a derivative. That's right, we're looking at the rate of change of volume with respect to time. You should always remember that the phrase "with respect to" will always indicate the dx of the derivative, as in the denominator of the derivative. Now we can write out what the question is asking for. What is dv over dt when h equals 5? Wow, would you look at that? The variables don't match up. It's time for the chain rule. Because we're already given dh over dt, we can rewrite dv over dt as dv over dh times dh over dt. We can solve dv over dh because we already expressed volume as a function of h back in part A. Therefore, dv over dt is equal to pi fourths h squared times negative 3/10. Now we can plug 5 in for h and write the answer as dv over dt when h equals 5 is negative 15/8 pi cubic centimeters per hour. Now for part C. Show that the rate of change of the volume of water in the container due to evaporation is directly proportional to the exposed surface area of the water. What is the constant of proportionality? First off, let's write down dv over dt. Now, they're asking us to show that it's directly proportional to the exposed surface area. First of all, what does that even mean? Directly proportional basically means that there's some sort of constant of proportionality, which is usually denoted as letters like K or C, that's multiplied by another formula in order to make both sides of the equation have equal proportions. When the question is asking us to show that they are directly proportional, they just want us to clearly write out the equation. In this case, dv over dt equals k times the surface area formula, which, as seen on the right circular cone, is just the area of the circle, or pi r squared. Writing this out will automatically give you 1 point in the FRQ, so we're off to a good start. All we have to do now is solve for k. Thanks to part B, we already know that dv over dt is equal to negative 3 pi h squared over 40, and thanks to part A, we identified that r equals 1/2 h. After plugging everything in, we get negative 3 pi h squared over 40 equals k times pi h squared over 4. As we continue simplifying this equation, we get k equals negative 3/10. So now we can conclude that the constant of proportionality is negative 3/10. And that concludes our review on related rates. Thanks again for tuning in to Collision Curriculum. Collision Curriculum is produced and directed by Rachel Rosal. Our script supervisor is Rachel Rosal. The show is written by yours truly, Rachel Rosal, and our graphics team is Rachel Rosal. Thanks for watching, and as we say in my household, never start a project that will most definitely take over 15 hours to do 2 days before it's due, because it is inevitable that you will not get any sleep for the next 24 to 48 hours.